let's roll here. Do you guys have some homework questions you want to talk about?
Yes.
All right. I don't know. It's like the news.
Wow.
That's a really interesting article.
Yeah, Luke.
Number 35.
This is from 2.6.
Yes.
Okay. Just so that everybody's on the same page. So 35. Okay. The limit as x approaches infinity of 1 minus e to the x over 1 plus 2 e to the x. Okay. And did you look up the answer to this, Luke?
I did.
Is it -2?
I think -1/2.
Oh, -1/2. Yeah, sure. Okay, no problem. So, you know what Mr. Kulik sees here? He sees the same degree, like this is the same function with the same rate of change. So all I'm doing is looking at leading coefficient over leading coefficient. Now, you want to see this algebraically. What I would do is I would multiply 1 over e to the x to the top and the bottom. So I'd have 1 over e to the x minus 1 over e to the x plus 2. And when I apply the limit to the numerator and denominator, 1 over e to the x is like 1 over big. So that goes to 0, minus 1, 0 plus 2, -1/2. That's how when I looked at it and I said the answer, like, I mean, other than goofing up the 1 in the numerator, forgot about it. But that's what I was looking at, was just like, it's the same rate of change, so just leading coefficient over leading coefficient. But there's algebraically what you would have done to get to the same thing. It's maybe a little bit more reasonable. Blake.
How did you get number 51?
50.
How do you like do it?
51. Okay. Let's see here. Let's do.
I got that far, and then I quit.
Okay, so this, what page is this on here approximately?
I don't know.
120, 142.
Wait, where'd you get this really fancy PDF?
This is literally the PDF from the.
Oh, yeah, no, okay. That's Adobe. Okay. Cool. That's a really cool. Sorry.
And then watch this stuff.
Oh, okay.
Screen clipping.
Oh dear. Dang. You're dragging. Dragging and dropping.
All right, because that was just a lot of words. All right, a function f is a ratio of quadratic functions, has a vertical asymptote of x equals 4. One intercept at 1, just one intercept at 1, and has a removable discontinuity at -1. Oh, okay. And then the limit is x approaches -1 is 2. Evaluate this. Okay. So my function, I know, is like ax squared plus bx plus c over ax squared plus bx plus c. And maybe I should write like a1, b1, c1, and a2, b2, c2, because they're different a, b's, and c's, right? Okay. If there's a vertical asymptote at 4, that tells me that my denominator must have contained a factor of x minus 4, right? If it tells me I have an x-intercept at 1, the numerator must have contained the factor x minus 1. If it says it has a removable discontinuity at x plus or x minus 1, then I know that there must have been a factor of x plus 1 in both the numerator and denominator. everybody so far so good? So if I FOIL this out, I have this. What I need to check now is that this piece to see if there's like an extra coefficient that's floating around somewhere. So if I look at the limit as x approaches -1 of, I'm going to do just k times, because there could be some constant stuck here somewhere. I know that's equal to 2. Is there any reason why I can't do oh, sure. Yep. So this is equal to 2. I can't do direct substitution as it's currently written, correct? But if I reduce, can I do direct substitution now?
Yes.
Okay, so let's do that. So that gives me -2k over -5 should equal 2. So the k here should be 5, right? So I'm going to say then, I don't need this part over here. I'm going to dump you. So this should just be 5 times this stuff. Now that I have my function written, the rest of this should be pretty straightforward. All right, zoom back out. Want to do f of 0? Well, okay. It looks like 5/4. You guys buy that? And then it says the limit as x approaches infinity of f of x. So here, I know that this is like 5x squared minus 5 over x squared minus 3x minus 4. Degrees are the same, so I can just write this as leading coefficient over leading coefficient. So it should be 5. I think by far the most challenging piece of that was just getting the correct f of x to come out, and building that guy out from the information that you're given. Does that make sense, Blake?
Right.
Tricky, right? But after we kind of talk through it, you should be like, oh, yeah, okay, vertical asymptote means that that kind of factor's got to be in the denominator. Okay, x-intercept, that kind of factor has to be in the numerator. Removable, okay, that factor has to be in both. And then we just have to worry about, is there a constant floating around somewhere in here? Luke?
So did you guess or know that there had to be a constant?
Well, because I have a1 over a2, or a1 x squared and a2 x squared. I haven't accounted for the possibility that there's like a greatest common factor in the whole thing yet.
Okay.
I don't know that the coefficient had to be 1. I just know that, okay, this part I knew,
Yeah.
but was there a greatest common factor in there at some point? That's what I didn't know, and that's what the limit was going to get me, was that greatest common factor. Paul?
Just like a general question.
Yeah.
Last year we'd get, like the reviews before the test. Are we gonna get like a review like that?
That's the plan. I haven't finished writing the test, and then it makes no sense to build a review before you build the test, right?
Yeah, no, I was
But,
just like,
yeah.
There's like a lot of, parts to this chapter. So
Absolutely.
I was hoping that there was something like kind of bring it all together.
Sure. Yeah, absolutely. Oh my God, Jack. I want to call you Josh for some reason. That doesn't.
Number 27, 2.6.
Okay. And I was like, Josh is not the right name. Stop for a minute before you make yourself look like a fool. But then, like, I sat there and made it look like a fool anyway. We did do this yesterday.
Not yesterday.
Cheating.
Okay, last class. So just,
I didn't need help with 51.
oh, where are my notes from last class? Oh, I did. I must have stuck them in with this, right? Yeah, okay. Bloop. Yeah, it's the exact problem we did yesterday.
Oh, I see what I did wrong.
Oh, good. That's even easier then, right?
Yeah.
It's okay. Boop. There we go. So we started by multiplying by the conjugate.
I simplified the conjugate.
Oh, that would do it, right? And again, I knew I was going to multiply by a conjugate because if I try direct substitution at this step, infinity minus infinity, that's indeterminate. I simplified after I multiplied the conjugate at this step. If I plug in again, I get infinity minus infinity in the numerator. That's indeterminate, so I knew we had to keep going. At that point, I noticed that it's kind of like the degree in the numerator was 1 and the degree in the denominator was 1. So I multiplied by 1 over x over 1 over x. I just wrote the 1 over x in the denominator so that I could push it into this radical. And after that, now that I got those x's out of there, now I can do the limits. And I just did the limit like piece by piece. So limit of a is a, limit of b is b, so I have a minus b on top. Limit of 1 is 1. Limit of a over x is 0, etc. So you can just push that limit through piece by piece.
Yeah. Thank you.
Sure. No problem, dude. Anybody else? Luke?
So for number 37,
Same section still?
yeah, same thing.
Okay. This is a good one.
What I did for it was I changed the e to the negative 2x to 1 over e to 2x multiplied by cosine. And then I just kind of was like, you know, how like the e to the x as x approaches infinity is just like 0. So I got 0 over cosine of x and just kind of put the answer is 0. Is that like the right logic?
There's one thing that we have to be careful about. So you're saying that you broke it up like this, right? And you correctly identified that this limit is 0. We don't know that 0 times everything is 0, because if that is infinity or negative infinity, that's an indeterminate form.
Okay.
So we do have to be careful there and think about what the limit of cosine as x approaches infinity is. What is the value of cosine bounded between, though? -1 and +1, right? So just doing this.
Yeah.
So no matter the actual limit as x approaches infinity of cosine x does not exist, because we're always oscillating back and forth between those two values. But the point is that that's finite. It's not going to infinity or negative infinity.
Okay.
That's the piece that we need to say then, okay, we do get 0. So we do need to be very careful, because 0 times infinity is not 0. That's indeterminate. So but yeah, you had exactly the right idea. Broke it up into the product of two limits. The first limit you can absolutely evaluate down to 0. That's correct. And we just had to be careful about that second limit and make sure that it wasn't infinite. We don't actually need to know what it is. We just need to make sure it's not infinite. Jack?
This is just me having a really bad memory, but
That's
for
okay.
33, arctan is tan inverse, right?
Correct. Yeah.
I could remember if that was
They are the same.
tan inverse.
Yeah. Or same enough for our purposes, right? I think there may be some like little small like domain thing or whatever, but it doesn't matter. Luke?
So for arctan, would you just have like a tangent graph and then you just kind of flip it on its side? Is that what the inverse would look like?
Yeah, let's just do it, right? So the way I would think about this is just like as a composition. Everybody's okay with that? And what is the limit as x approaches infinity of e to the x?
0.
Nope. It's infinity. If it was going to negative infinity, Luke, it would be 0.
Okay.
Right? But if you think about the graph of e to the x, it's exponential. So as you're going to the right, you're actually growing as really as fast as possible. Like that's exponential is the fastest changing function type. So that's, we don't want to write this though. This is like super bad form. So what we'll say instead is that the limit as, I'm going to create a new dummy variable t approaches infinity of arctan of t, right? So if e to the x is going to infinity when x approaches infinity, I'm just going to create a t there and have t going to infinity to kind of hold its place. The AP grader will like this much, much better than you putting an infinity in there.
Yeah.
Jack?
So t is representing.
Yeah.
Okay.
T is essentially like e to the x,
Oh, okay.
right? So t, the limit as t going to infinity is the same thing as the limit as,
Or T is the limit of.
right? Let me say that. That's basically all I'm doing. Is that okay?
Okay.
So that's like a little aside, right?
And that's just for.
That's to make the notation make sense,
Okay.
right? Because I can put the infinity in there and you guys know what I mean. And I'll probably do that on occasion, but I also want to make sure, especially early on, to like, what we're doing there is not really proper looking mathematics. That outside of this room, while that makes sense intuitively, it's like really bad form. And I don't think that like on a problem that was graded by the AP, they would like that at all. But this is the way you work around it, is you just create like a dummy variable to go to infinity in its place. So this is one. Now, I could evaluate this with the graph. I could use a table. Any of those things are fine. And that's, I would probably just use the graph to do this. So just tan inverse of x. And then we'll assume trig that. Oops. Yeah, okay. And if I do my trace and I trace along here, and that's probably just not wide enough because we got to go to infinity, so maybe let's just make that 100 out there. But certainly looks like there's some asymptote going on here. If I go and I look at that y value, 1.55 should look an awful lot like pi over 2, right? Something a little more than 1.5 is probably pi over 2, particularly when we're doing trig stuff. So that is correct. That is what you're looking for. And the other way that you could have thought about this without having to use your calculator and just use like our prior knowledge. If I think about the graph of tangent, I know tangent has an asymptote at pi over 2 and is going towards positive infinity there. So the tan inverse at infinity should be pi over 2, right? So the input of tangent would be the output of tan inverse, and the output from tan inverse would be the input, or the output from tangent would be the input for the tan inverse, right? So like tan of pi over 2 equals positive infinity implies that tan inverse of positive infinity would equal pi over 2, right? Now that's how you could have done this with no calculator at all, but it relied on remembering what the graph of tangent looked like, and maybe you remember that, maybe you don't. But conceivably, that's information that you had at one point, right? Anybody else with questions that we want to talk about? These were all good ones, guys. Okay. Let's pick up where we left off on 2.7. So I want to go back and think about physics here a little bit. Remember at the very first day of class, what was the motivator for developing calculus? Yeah, it was Newton wanting to find a way to calculate instantaneous velocity so that for his work on gravity, right? So let's say we have some position function here. So the position functions, the y-axis is going to give us a distance. The t-axis would be a time, right? And let's say we just have like some object we've thrown straight up and it's come straight back down. Everybody's okay with that? If I want to calculate the instantaneous velocity at every point of this function, I'm basically just taking the slope and of the tangent lines and then graphing those per unit time, right? So the y-axis now is going to be distance per time, and the x-axis will still be time. So that'll be like a velocity graph. So then my function would look like this. And if I wanted the instantaneous velocities, what is that called? The change in velocity is? Acceleration. Great. So again, those are change in velocity per unit time, so the change in distance per time squared. And notice here, if I try to draw tangent lines for this velocity graph, all these tangent lines have the exact same slope, right? They all have negative slope, so like my acceleration would look like that. Everybody's okay with that idea? So what we're noticing is that velocity is like the instantaneous rate of change or the velocity at a time is the instantaneous rate of change of position. And acceleration at a time is the instantaneous change in velocity, and so on, right? Everybody's okay with that idea? So remember yesterday, we talked about the derivative at a point that we could use to find, or could be found using this. Oops. What's that? Oh, that's the notation for a derivative? Did we do that yesterday? Did I not say that? Oh, that's because... Did I not? Oh, okay. Fair enough. We didn't... Oh, I didn't have... Oh, it just hasn't happened in the notes yet. Why was I trying to use this notation already? I don't know. Well, okay, so when we talked about the slope of a tangent line, we just had this equation then, right? At some point A. Everybody agree? Okay. And we see that the velocity at some instantaneous velocity at point A is the same as, or is the same thing, right? It's just a collection of tangent line slopes. The point of this is that it's the exact same thing, right? So if I wanted the instantaneous, if f of x is my position function and I want the instantaneous velocity at a, it's just the slope of the tangent line of f of x at that point a. It's going to be the same thing, right? And if I have a velocity function, then my instantaneous acceleration at a is, well, it's the same thing, right? So the slope of a tangent line, the instantaneous rate of change, all of these things are all mean the same thing. We're going to give this thing now a name, a proper name. It's going to be called the derivative. So we'll start and guess what the formula is? The same thing, right? Now, is this all kind of feeling like the stuff that we have done in 2.1 and 2.2 still? We're just doing like slopes, basically. That's all we're doing. You're dead on with that. Okay. So let's do a quick example here. Say we want say we have f of x is the function, where did you go? X squared minus 8x plus 9. And we want that and then, okay, then we'll ask for f prime of 3. So f prime of 3 is the derivative of our function f of x at 3. So I'll apply my definition. So the a here is 3 Everybody feel good? What I've done so far? Oh, shouldn't, because I didn't write a 3 there. All right. So now, how do I do f of 3 plus h? I'm going to plug 3 plus h in for the x's in f of x, just like I would for like a composition of two functions. And then how do I do f of 3? I'm just going to plug 3 in for x. Everybody's okay there? What do I have to be careful about here? Got to make sure I distribute my negative with the subtraction symbol there. Very easy to forget about that. It's a very Algebra 1 mistake, but it's a very common Algebra 1 mistake. That's why I'm reminding you guys about it right now. Is everybody cool with how I plug things in? All right. Again, I want to point out that if I had done direct substitution prior, I would have gotten 0 over 0, something indeterminate. If I had gone back to here and plugged it in. So I'm going to keep going trying to simplify this. The natural thing to do to simplify this would be to just multiply everything out and try to combine like terms and see what we got from there. Is everybody cool with that? Okay. So I foiled everything out, distributed everything through. What do I see? I see I have a plus 9 and a minus 9. Minus 24, a plus 24, plus 9 and a minus 9. So those all combined and kind of canceled out. Of the things that are left, what do you notice about the pieces that are left? I have a 6h, an h squared, and a negative 8h. They all contain an h. So we can reduce. Yeah, if you want to factor the h out and then reduce, or you can just reduce piecewise like I did. Either way is fine. And then we can direct sub to get negative 2.
So is that right there the derivative?
That's the value of the derivative at 3. So that's the value of the derivative of f at 3, at x equals 3. It's exactly right. Okay. Let's do another example. So D of t is the US debt at time t. The table there gives approximate values and end of the year estimates in billions of dollars from 1985 to 2010. And we're asked to estimate the derivative of D at 2000. Notice the direction. What are we trying to do with D prime of t? Estimate. Can I calculate D prime of 2000 precisely? Can I get that instantaneous rate of change from the information I'm given? No. I'm just going to be able to create an estimate. What's going to be the best estimate I can create? I'm going to look at these two average rates of change and then take the average of those. Is everybody okay with that plan? Very similar to things that we did in 2.1 and 2.2, right? Okay. So I'll do the slope from 1995 to 2000 first. And we'll go the slope from 2000 to 2005 second. So I'll say M2000 is about 134.70 plus 501.64 divided by 2, or about 318. 318 watts, though. This is a story problem. It needs a well, it's a rate, right? It's a rate of change.
Per year?
Yeah. So what is this derivative really saying? In the year 2000, the national debt is increasing or decreasing? Increasing, because it's a positive number, by $318 billion per year. So like that's the kind of, like, if somebody asks you to interpret the meaning of the derivative, that's kind of what they're asking you to do, is to write out in words and context what it means. So this is from like the 2000, in the year 2000, is that, right? The national debt piece comes from, that was the meaning for D. And then the rest of this is just coming from what we did back there. What do you guys think? My opinion, I think 2.6 is maybe the, especially in consideration of the things you've done prior to this, is maybe the easiest section in chapter 2. Considering you've already done 2.1 and 2.2 at this point, you should feel pretty comfortable doing these slope kind of things. So this is the 2.6, I'm sorry, the 2.7 assignment. What do I got here? 1, 5 through 9, 11, 14, 16 and 17 and 19, 22 to 23, 27, 29 to 31, 33, 39, 41, and then 46 to 47. Does that do this weekend? No. Yeah. I think 2.5 and 2.6 is the only thing due. Most of these are super quick. Most of them are super quick.
Wait, so was that all in everything in 2.7?
Yeah. Short section.
Wow, okay.
Right? We did a little bit yesterday.
So is there a review date now?
We have 2.8.
No.
2.8 is the derivative of a function. Well, that was we talking about. Yeah, we were talking about derivative as a rate of change. We're finding specific values of a derivative. It's a circle, man. It rolls. Okay, so remember that we have a derivative of a point, which is this guy, right? We just talked about that. But what if I don't want to find this for a specific A? Or what if I have like a whole list of specific A's that I want to do? Can I do this once generally and then plug in my values for A afterwards? Yeah. Yeah. And this form that we've currently written it in, remember there's a couple of different ways to kind of write this, but this one with the H is particularly helpful if we're going to do this kind of in general. So if we let A vary, what do we call that when something varies? Variable. And I'm going to use X then as my variable in place of A. And we call this guy the derivative of F. So let's first start with something a little bit simpler, a little bit more intuitive. So here's my function f of x, and we're going to try to sketch in the graph of the derivative kind of on this same set of axes. Okay? So the easiest way to do this is going to be to start by identifying the place on f where the slope of the tangent line is 0. How many places do you see where the slope is 0? 3. Great. Where are those 3 locations? The extrema, right? Yep. That's the technical term you're looking for. I knew what you meant, though. So I know f prime is going to have zeros at those locations. Everybody cool with that? Okay. So now I'm just going to go section by section of my graph. This first section, the slope is negative, right? So the graph of my derivative should be below the y-axis. Everybody cool with that? I'll look at the next section here. The slope there is positive, and so my derivative should be above the y-axis. Yeah, I'm sorry, x-axis. Thank you. Yep. Now, does it matter how high I'm making these things? I mean, you could go and try to like draw in a tangent line and like estimate, okay, from like here to here, the slope's like 10 or whatever, and try to do that. But like, you know, I don't know, maybe you should do that. Slope there got pretty big in the middle, right? Like over here, we're pretty darn steep. But I'm going to be honest with you, like if it's me grading this, I'm just worried about that you have the zeros in the right places and the graph is on the right side of the x-axis, or the correct side of the x-axis in each section. Okay, I look at the next section. We are negative, and probably doesn't get quite as steep there, so maybe I won't make that as steep or as low. You guys agree with that? That first section seems steeper, so it should be a little higher. And then my last part of the graph, positive, and so I don't know, like that. Looks good to me. Pretty easy though, right? No calculation to do. We just had to make some observations about what the graph looks like or whatever, and all right. Let's do some more computational examples then. If I want to find the derivative of f of x, well, let's just start with our derivative formula. Everybody okay with that? So when I do f of x plus h, what does that mean? Plugging x plus h in place of the x's in f of x. Oh no. And then if I have f of x, what does that mean? Just f of x. Notice that I'm being careful to put that in parentheses, because what do I have to be careful about? Yeah, distributing that negative, right? Again, very easy Algebra 1 level mistake to make, but I'm saying it because these are the kind of mistakes that are not calculus mistakes that create big, big problems when you try to do stuff like this. You know what I mean? All right. Again, I want to point out that if I was back here and I tried to direct sub, I'm going to get 0, right? So I'm going to have to do something to do this, to be able to evaluate this limit, what should I do? When I multiply everything out and try to combine like terms, like I can't really do anything else before I do that, right? Feels like a good idea. Remembers the binomial expansion formulas. If you don't remember your binomial expansion, that would have been a bugger right there to handle. Mr. Kulik's got your back, though.
Good to hear.
The coefficients in a binomial expansion are just that row of Pascal's triangle. So like Pascal's triangle, you just add the two values above it. So like for cubed, the coefficient should be that times whatever the, the other two terms are. But okay. If we look at what we got here, let's combine some like terms. I notice I got an x cubed and a negative x cubed. I have a negative x and I got a positive x. What else do you guys notice?
All the rest of them have H.
Everything else has an h in it. So that can all reduce. Oh, Mr. Kulik, is that always going to happen? That h has got to get out of there somehow, guys. Unless you've made a mistake, that h should be gone bye-bye. And if I direct substitute now, since there's no h in the denominator, I'm done. So we'd say that f prime of x is equal to 3x squared minus 1. All right. That ain't bad, right? I mean, it's just a bunch of algebra. Like the calculus part wasn't bad. Jillian. Certainly. All right, who wants to do another? That feels like something we should want to practice a couple of times, right? Let's try little old f of x is equal to x squared. That sound okay to you guys? Okay, well, we start the same way with just our limit definition, or our derivative definition. And we'll plug our values in. What am I going to need to do to simplify this? Yeah, use the conjugate. Absolutely. So what do we got now? The limit as h approaches 0 of x plus h minus x over h times x plus h plus, or square root x plus h plus square root x. Everybody cool with how I multiplied the conjugate out there? Let's start simplifying or combining like terms. In the numerator, I notice I have a plus x and a minus x. What's left now in the numerator? Just an h, so we can reduce that. So I have 1 over square root of x plus h plus square root x. Can I direct substitute that? Yeah. So when I do that, I get 1 over 2 square roots of x. Am I going to rationalize the denominator here? No, thank you. Just going to leave that guy right the way he looks. He is fine by me. Everybody's okay there? All right. Hold on to your butts here for this one. What's going to be the problem here? We're going to have fractions inside of fractions, and lots of x's plugging in. It's going to get a little messy, guys. Going to get a little messy. But it's just algebra messy. The calculus part is pretty easy, because all I have to do is a limit, which is not so bad. Right? I can use direct substitution on the limit. I just have to get it to a point I can direct substitute it on. All right, let's start plugging stuff in. What is f of x plus h? I distributed the negative when I did that automatically. Is everybody okay with that? What's this called where I have fractions inside of fractions? You guys remember the name for that thing? It's called a complex fraction. It's not fracception, which is what I wish it was. Or you have like dreams inside a dream, fractions inside of fractions. Do people still like Inception? I don't know. It was a cool movie back, 10 years ago or whatever. 15? It's been a while. It's still quite stylish, though. All right. Do you guys remember the easiest way to deal with a complex fraction?
Of course.
I wouldn't do that.
Oh.
You could, but I think it's going to make it messier.
Go to the next problem.
I'm going to multiply the top and bottom by the least common multiple of all the denominators. That's what I would do. And the reason I like to do that as my way to deal with the complex fraction is that it gets rid of the fractions inside of fractions the fastest, which I would rather get rid of that and be gone. All right, so when this distributes to here, I notice that the 2 plus x plus h's are going to cancel. So what I'll be left with is the numerator times that other 2 plus x piece. Is everybody okay with that? So I have the numerator that's left, and then the 2 plus x piece that hasn't canceled.
Oh, you're showing
Just that first piece. And then I distribute it to here, the whole thing. And the same kind of thing happens. I have the numerator and then the piece that doesn't cancel. And I like doing it that way because what do you notice immediately has happened? There's no more fractions inside of fractions. That's the way I like to do it because it gets rid of the fractions as quickly as possible. Let's just get on with our lives. All right. What is Mr. Coolit going to do now? Who votes to FOIL this all out? Yep, that's the correct answer. Who says that, but Mr. Kulik, that's going to be like a colossal hassle because one of those things has 3 in it, so it's going to be like really difficult. You're right. It is a hassle. Ugh, Mr. Kulik, are you joking? Can I trust that you foiled that out correctly? Oh, I forgot the other stuff too. Yes, thanks, John.
Foil it all out in your head.
No, I have it all on the piece of paper here in my notes.
That's impressive even for you.
I always wonder how you like just instantly foil it.
Some of the stuff I am foiling in my head. This one I wrote down because I'm like, I think I'd mess that up if I tried to do it in my head. It's not so bad because nothing combines, at least. So it's just like, you just got to make sure you get all the pieces.
So none of this actually like.
Well, no, I mean like when I foiled those two together, like there's no like terms afterwards to combine together.
Why didn't you foil out the bottom half?
Because I'm hoping I'm just going to be reducing next.
Okay.
And to reduce, I need it in a factored form anyways.
That's right.
So I figured if I need to foil the bottom out and there's no, I can always do that later. All right, so I'm going to distribute through the negative, but I'm not about to recopy that just to distribute through that negative. So I'm just going to do that because, like, give me a break. I'm not doing that again. And then let's combine some like terms. So I have minus 3h over, well, that certainly is a heck of a lot nicer, right? It's not so bad now that I mean, it got real bad there, but it came on back down to earth pretty nicely for me. And now I can direct sub to get negative 3 over 2 plus x times 2 plus x. And if you want to write that as 2 plus x squared in the denominator, that's okay too. Whew. Those quotients, man, they're a doozy.
Great way to describe it. So,
Yes.
So just to the easiest or the best way to get rid of those fractions of fractions is you take the set with the greatest denominator, right?
You take the least common multiple of all the denominators.
Least common multiple of all the denominators.
So why don't you further factor it down to x squared plus 4x plus 4?
You could. It's not wrong.
Okay.
It's the same thing, right? You're talking about the same thing. You didn't make it any simpler. You just wrote it in you just wrote it in a different way, which is fine. Still right. I typically don't multiply things out if I don't absolutely have to, because it's just it's less foiling that I have to do. But Paul, sure.
So the least common multiple of all the denominators, and then you multiply it by into the numerator and denominator.
And that'll clear all the fractions out.
Okay.
And you'll be free and clear from there.
And then on the step below that, how did you know that 1 minus x minus h would just stay the same and then 2 plus x would go there?
So when I did this distribute, this piece canceled.
Oh.
and I'm left with just the numerator that was there and the other piece that didn't cancel.
Okay.
And the same thing below. So that's all I'm looking at is just like, I have everything except the stuff that canceled.
Gotcha.
Teagues.
Why did you distribute the negative in the first fraction but not in the second one?
Well, if I have like three numbers multiplied together, say like I have, if I have -2 times 3, that's just -6, right? It's not the same thing as -2 times -3.
Yeah.
That's fine,
Okay.
right? So the negative just goes, you can distribute it into one fraction, or you can do the multiplication, distribute it all at the end. That's what I did, is I just foiled and then distributed the negative all at the end.
Okay.
But you could have distributed the negative into the first one or the second one, but not both. And that would be okay too. Does that make sense? John?
You got fractions in the numerator and denominator. You have to do this twice.
Well, you shouldn't get fractions in the denominator because the denominator is always just going to be h.
Like not in this
But
scenario.
no, if you do the least common multiple of all the denominators,
Oh, so every
numerator, the stuff from the numerator and from the denominator,
Yeah.
the upper level and the lower level, if you take the least common multiple, every denominator, one time clears out all the fractions,
Okay.
and you should be in a much better place after you clean everything up. So that's, again, really nice way to deal with the complex fraction rather than trying to make a common denominator in the numerator, combine all those like terms, and then multiply by the reciprocal. It just, you have to carry those fractions for a long time doing that. I'd rather just get rid of them right away and deal with cleaning up the leftovers after that. I find that I'm much less likely to make a silly mistake in those sort of situations. Okay. Let's just stop here. This feels like a good stopping point because I got fifth hour closer to us. They're just 2 examples apart now, so that's a good place to stop here.
Are we behind?
No, you guys were ahead,
Nice.
and I